Now we can start.
Okay, thank you. Let's start. So let me finish the proof of the criterion of affinity for a spherical variety, which I recall here at the first page, at the first slide. The theorem says that a spherical variety X is affine if and only if it satisfies several conditions, 5 conditions. So first of all, it is simple. Secondly, the cone spanned by the cone corresponding to the closed orbit, and all colors and vectors corresponding to all colors should be pointed. These vectors corresponding to colors all should be non-zero. Also, the cone corresponding to the closed orbit should be the largest face of this cone C, whose relative interior intersects the evaluation cone. And finally, the set of colors containing the closed orbit, the part of the color data of this simple spherical variety, this set of colors should be exactly the set of colors whose corresponding vectors belong to this face, C sub y. Okay, so we have proved. So coming back to the proof. We have already proved the implication from the left to the right, and now let's prove the converse implication. So we want to prove that a spherical variety satisfying these 5 conditions is affine. Our first step is to consider the coordinate algebra of this variety X. The algebra, better to say, the algebra of regular functions. We don't know so far that it is affine. It is not quite correct to speak about coordinate algebras. So this algebra of regular functions is the direct sum of simple G submodules, which we usually denote as K of X with subscript lambda in brackets, where lambda runs over the lattice vectors in the dual cone, C check. This is because the condition for the weight lambda to belong to C check is exactly the condition that the corresponding B semi-invariant function F lambda has no poles along all B stable prime divisors in X, because the cone C is generated by all vectors corresponding to the B stable prime divisors. Those vectors which correspond to G stable prime divisors belong already to this cone C sub y. Yeah, all G stable prime divisors contribute to this cone. And also all colors, all B stable prime divisors which are not G stable, the respective vectors are included in the set of generators. So the condition for this lambda to belong to C check is exactly the condition that the evaluations corresponding to all B stable prime divisors, both G stable and not G stable, all these valuations take non-negative values on the respective B semi-invariant function. And this exactly means that this function has no poles along X, and so far it is regular on X. This is about B semi-invariant functions, but you know that the algebra of regular functions is a direct sum of simple submodules. And each of these simple submodules is generated by its highest weight vector, which is exactly the semi-invariant function whose weight satisfies this property. So, yes,
Professor. Do you mean that the decomposition of regular functions on X into simple G module, the highest weight satisfies that the weight belongs to C check?
Yes, yes, of course, of course. This is a decomposition. This is our standard notation. This is a decomposition into the direct sum of irreducible highest.
This decomposition apply to any G variety, or any spherical G variety, right?
Yes, yes, of course, of course. So far, we use only the condition that this cone C is generated by all vectors corresponding to B-stable prime divisors, both colors and G-stable valuations and G-stable divisors doesn't matter. We just take for C the cone generated by all, you can say the cone generated by all B-stable prime divisors. And if you take such a cone for any spherical variety, then you get the algebra of regular functions decomposed as here. You are right. So far, we used only this. This is not even a condition, because the condition is that this cone is point. We just use the definition of this cone to write this decomposition. Okay. So this algebra is actually a finitely generated algebra. Finitely generated algebra. For instance, it is generated by the direct sum of this kind of submodules, say K sub x lambda 1 plus etc. plus K sub x lambda m, where this lambda 1 lambda m lambda 1 etc. lambda m are generators of the semigroup of lattice vectors in the dual cone of C check intersect with lambda.
So this is the application of Gordon lemma, right?
The application of Gordon lemma is that this semigroup is finitely generated, so we can pick finitely many generators. And the claim that the irreducible G submodules corresponding to the generators generate this algebra, this is because from this direct sum, you can recover all highest weight vectors, because any highest weight vector whose weight belongs to this dual cone is a product of highest weight vectors with these weights to some powers, to some non-negative powers. And therefore, the subalgebra generated by this direct sum contains all highest weight vectors of all irreducible submodules in here. But this subalgebra is also G-stable, and therefore it coincides with the whole K of x. This is the argument. Okay? So we have this finitely generated algebra.
So every summand in this formula is one-dimensional, right?
No, because this is not the highest weight line. This is the whole irreducible G submodule. It contains a one-dimensional subspace generated by this lambda I.
So why is this a finitely generated? Well, finite because
each of these summands is finite dimensional. It is a simple G submodule of the respective highest weight. So each of these summands is finite dimensional, and the whole sum is finite dimensional. You can just take the basis, any basis of this direct sum, and it will be the set of generators.
Generate because it is G-stable and it contains every highest weight vector, right?
Exactly. Okay, so I'm sorry, I think I have to erase this page because it is, sorry. Yeah. This implies the fact that this algebra is finitely generated implies, of course, that there exists an affine G variety. There exists an affine G variety say x prime, whose coordinate algebra is exactly this algebra, just what is called the spectrum of a finitely generated algebra. Okay. Now the second step of the proof is to show that the diffraction field of the algebra of regular functions on X is the whole field of rational functions on X. Recall that we don't know so far that X is affine, so this is a non-trivial statement. Actually, we have already proved a similar statement when we considered a simple spherical, when we constructed a simple spherical variety from a colored cone. Here, the idea of the proof is the same. Actually, the proof is more or less the same, but let me recall it for you because it was some time ago. So to prove this equality, it suffices to prove
so the existence of x prime is due to the finitely generated.
Exactly. Yes, absolutely. Absolutely. So it suffices to prove that the diffraction field of the algebra of regular functions on X contains the algebra of regular functions on the open B orbit. Because this open B orbit, Y upper naught, is an affine open subvariety, and its field of fractions is exactly the field of fraction of rational functions on the whole X. So it suffices to prove this inclusion. Now we want to use the condition that the cone C is pointed. So since it is pointed, we can pick up a weight lambda, a lattice vector belonging to the dual cone, which takes strictly positive values on all vectors in the cone C except 0. So on the picture, you can imagine this lambda as such a vector. So the hyperplane on which lambda vanishes intersects the cone C only at 0, and the whole cone C lies on one side of this hyperplane. So this vector lambda, this weight lambda, satisfies the property that its pairing with all vectors in C except 0 is strictly positive. And this means that the order, the vanishing order of the respective semi-invariant rational function along each B-stable prime divisor in X is strictly positive. Because this vanishing order is exactly the pairing of the weight lambda with the respective vector Vd bar corresponding to the divisor D. And all these vectors Vd bar are non-zero because of this condition. This condition is for colors, and for G-invariant, for G-stable divisors, we already know that the respective vectors are non-zero from the general theory. So all these vectors are non-zero, they are the generators of the cone C. And since lambda takes strictly positive values on all vectors in C except the 0 vector, it takes strictly positive values on all these Vd bars. So we get this condition. And this means exactly that the function f sub lambda has zeros along all G-stable, all B-stable prime divisors in X. And by therefore, by multiplying, so let us take any function f, any rational function f, any regular function f on the open B orbit in here, let us take any function in here. Since this function is regular on the open B orbit, its divisor of poles is B stable. It is on the boundary of the open B orbit. Therefore, by multiplying f with a sufficiently big power of f lambda, we can kill the poles of f. So we can obtain that this function is already regular, has no poles, for sufficiently big D. And also the function f lambda itself belongs, sorry, I didn't want to write what I just have written. The function f lambda itself, I'm sorry, I think that, yes. Yes, exactly. So the function f lambda itself is regular on X because it is semi-invariant. Its poles can be only B stable, but we have chosen this function in such a way that it has no poles, it has zeros along all B stable divisors, and therefore it is regular on the whole X. And from these two inclusions, you see that the function f is in the field of fractions. The function f is in the field of fractions of regular functions on X. So this implies that f belongs to the fraction field of regular functions. Okay. So we have proved that the fraction field of regular functions is exactly the field of rational functions. This implies, now we come to the final step of the proof. This implies that the natural map from X to X prime, we have such a map because K of X prime coincides with K of X. So a map to an affine variety is given by a homomorphism from its coordinate algebra to regular functions on a given variety. So in this case, this homomorphism is just the identity because these two algebras coincide. So we have this map from X to X prime. And since the fraction field of K of X prime is the field of rational functions on the whole X, so the fields of rational functions coincide. They are, you can say they are isomorphic. This means that this map is a G-equivariant birational isomorphism. G-equivariant birational isomorphism which extends the identity map on the open orbit. Because it is G-equivariant, then the open orbits are isomorphic to each other, and we can identify them, just identify them. Okay, so we have got an affine spherical variety with the same algebra of regular functions as it was for X. Now, by the first part of the theorem, by the implication from the left to the right, which we have proved on the previous lecture. So if we have an affine variety, then we have these 5 conditions. By this implication from the left to the right, we can say that this X prime is simple. So it is a simple spherical variety with a closed orbit Y prime. And the cone generated by the cone of Y prime and all colors
by what implication? Oh, X prime is affine. Oh, I see.
X prime is affine, yeah, by construction. And the cone generated by the cone of Y prime and all colors is exactly the cone C, which we have started with, is exactly this cone. Why so? Because the dual cones coincide. Because the dual cones coincide.
Professor, I have to ask a question. Sorry.
Okay.
So why it suffices to prove that the fraction field of Kx contains Ky upper north? That
well, because this Y upper north is.
Did we use that Y upper north is affine?
Of course. Y upper north is an open B orbit. The orbit of a solvable algebraic group is an affine variety. It is always the case. And already we use this claim. So the fraction field of this guy is the field of rational functions on Y naught. And it is the same thing as the rational functions on X.
Yes. So we use that Y upper north is affine. I see.
Exactly. So let me come back to the end of the proof. We see that these two cones coincide because the dual cones coincide. And the dual cones coincide because the dual cones are recovered from the coordinate algebras, from the algebras of regular functions, because of this decomposition. So you see that the dual cone of C is exactly the set of let me say the set of lattice vectors of the dual cone is exactly the set of weights such that the respective semi-invariant function is regular on X. And the same holds for X prime, of course. So since the coordinate algebras of these two guys coincide, the respective semigroups coincide. And since the respective semigroups coincide, the dual cones coincide. So the dual cone of this coincides with the dual cones with the dual cone of C. And since the dual cones coincide, the cones themselves coincide. So this is the argument here. And now we see again from the conditions, now from these conditions, from these two last conditions, yeah, we see that the colored cone of the closed orbit Y prime. So this implies that the colored cone for the closed orbit Y prime in X prime, excuse me, sorry, just a moment. The colored cone of the closed orbit Y prime in X prime coincides with the colored cone of the closed orbit Y in X. Because these two colored cones are recovered from one and the same cone C as the largest face of C with relative interior intersecting the evaluation cone, and the set of colors is exactly the set of colors belonging to this face. So for both Cy dy and Cy prime dy prime, these two conditions hold. For X and Y, they hold by assumption because we assume this condition. And for X prime, Y prime, they hold because this variety is affine, and we already proved the implication from the left to the right. So these two conditions also hold. And the cone, this cone C for X and X prime is the same. So we have two simple spherical varieties whose colored cones coincide, and by the uniqueness theorem, this implies that these spherical varieties are isomorphic. So finally, we have proved that our spherical variety X is isomorphic to X prime, and therefore it is affine, because X prime is affine. This finishes the proof of the theorem. Excuse me. Something lights. Oh, I see. Sorry. Yeah. Yeah, so any questions on the proof of this theorem, on the end of the proof of this theorem? If not, we can go further. Okay, it seems that there are no questions so far. Now we turn to the applications of spherical varieties. Our first application will be in the theory of algebraic monoids. Algebraic monoids. Algebraic monoids are a natural generalization of algebraic groups. What is a monoid? Monoid is a semi-group with unity. We do not require that the inverse of each element exists, but we require associativity of the multiplication law, and we require existence of the unity elements. So we get a semi-group with unity instead of a group. Or a semi-group with unity is also called monoid. And algebraic monoids generalize algebraic groups. Instead of requiring an algebraic variety to carry on a group law, we require only associativity of the multiplication and existence of the unity element. And also, similarly to algebraic groups, we consider only affine algebraic monoids. So recall that by an algebraic group, we assume an affine algebraic group. An algebraic group which is at the same time an affine algebraic variety. The same restriction is reasonable for algebraic monoids. So let me give you a formal definition.
For the last page. Oh, sorry. I was.
Okay. Let's turn to the last page. Yeah.
So we have the colored cone of X and X prime is the same.
Yes.
But we do not know that X is simple.
We know this is by assumption, because we prove from the right to the left, we assume that it is simple.
Yes, the assumption. Oh, I forget that. Thanks.
Okay. So let's continue. We define an algebraic monoid. We define an algebraic monoid to be an affine algebraic variety. Which is at the same time a monoid. Monoid is the same as a semi-group with unity, as I told before.
So why should we require the affinity?
Well, for the same reason as in the theory of algebraic groups, because we get an interesting group or semi-group structure in the affine case. In the say in the projective case, we just get a billion varieties. So they are interesting from the geometric viewpoint, but they are not interesting from the group theoretical viewpoint. But let's just take this as an assumption. So monoid is the same as semi-group with unity. Let me denote it by M. And the relation of these two structures, the structure of an affine algebraic variety, so let me emphasize this assumption of affinity, not to forget. The relation of these two structures of an algebraic variety and of a monoid is that the multiplication law is a morphism. So this M is such that the multiplication law sending a pair x comma y to the product is a morphism. Actually, the same definition as for algebraic groups. Of course, the basic example, as in the theory of algebraic groups, we had the basic example of an algebraic group to be GLN, the full linear group. Here, the basic example of an algebraic monoid is, of course, the monoid of all square matrices n by n. Clearly, the definition of an algebraic monoid is satisfied in this example.
But this space, I think this space is isomorphic to the n square dimensional affine space. I mean,
of course.
how to make them different? I mean this, because algebraically.
What do you mean different? I mean this is not just an affine space of dimension n to n square. This is an algebraic monoid. It is equipped with a multiplication law because you can multiply matrices. Yeah. So we have this multiplication map. And this map, of course, is a morphism because you know the formula for multiplication of matrices. It is a polynomial formula. So this multiplication map on matrices is a morphism, and therefore this affine space comes equipped with the structure of an algebraic monoid. This is just what I wanted to say. Okay. In fact, we have the following. Any algebraic monoid M, say M, can be embedded as a closed submonoid in the monoid of square matrices of some size.
Closed embedding.
Yes. You know from the theory of algebraic groups that any algebraic group can be embedded as a closed subgroup in some GLN. And absolutely the same fact holds for algebraic monoids, for affine algebraic monoids, of course. But we assume affinity already in the definition. The proof of this fact is more or less the same as the proof of a similar fact for algebraic groups. So I can refer you to, say, in fact, to any manual, to any textbook in algebraic groups, but you can take, for instance, the book of Humphrey. Excuse me. The book of Humphrey. Linear algebraic groups, which is one of our standard references for the algebraic group theory. And in this book, you can take. Excuse me. I didn't hear you well.
I will ask the question when you write over.
So what is your question?
My question is, since you define algebraic group in this class to be linear, there is no use to say that any algebraic group is embedded into some.
If you remember, I defined an algebraic group to be affine. If you come back to some of the first lectures, I defined an algebraic group to be just affine. not linear, just affine. But affine implies linear. This is the fact, the respective fact for algebraic groups. Affine implies linear. And the same fact holds for algebraic monoids. So you may say that any affine algebraic monoid is linear.
I remember that.
Okay,
I see.
And here I give you a reference. This book of Humphrey, Linear Algebraic Groups, section 8.6. In this section, you can find a proof of the respective fact for algebraic groups. So if you replace M with an algebraic group G, and if you replace the monoid of all matrices with the group GLN of non-degenerate matrices, then you have a similar fact, and the proof is here. You can just take this proof and apply it more or less without changes to this case. Well, maybe with some obvious corrections. So I won't elaborate on this proof anymore. We can, in fact, we can just take this for definition of an algebraic monoid. We can assume that it is linear by definition, but I don't want to do it. I just wanted to stay on a bit more general, formally more general viewpoint, but in fact it is the same. Okay, well, so with any algebraic monoid, we can associate an algebraic group, which is just the group of all invertible elements in M. So the group of invertibles let me denote it simply by G, or by G of M, if I want it to be associated with an algebraic monoid M. It is by definition the set of all elements in M such that there exists an inverse element in M, whose product is the unity element. In fact, if we embed an algebraic monoid M in some monoid of matrices, n by n matrices, if we consider an embedding like this, then the group of invertibles is nothing but the intersection of M with GLN. It is obvious that the left-hand side is included in the right-hand side, because if you have an invertible element of M, and if M is a submonoid of matrices, then of course this matrix should be invertible, of course, yeah? But also the converse inclusion holds, and it is an exercise, an easy exercise for you to prove this converse inclusion. So exercise 1. For you is to prove this inclusion here.
Well, this M is the M that has a closed embedding into some n-dimensional matrices, right? Or it is the whole n-dimensional.
No, it is just no. Of course, not the whole. It is just a closed subvariety, a closed submonoid, a closed subvariety.
Oh, I see.
Yeah. A closed subvariety containing the unity matrix and closed under multiplication of matrices. This is the requirement. Okay.
I mean,
so this.
What is GLN respect to M? M is the closed subvariety of MATN, right?
So you have the space of all n by n matrices. You have an open subset in this space. GLN is open in here, right?
Yes.
And you intersect this GLN with a closed subvariety M.
Oh, M is just M, not the whole affine space. I see.
Yeah. No, it is this M, which is embedded in here, not the whole affine space. It is an algebraic monoid. It is, I mean, yeah. You just embed. This is not this example. This is not in this example. This is a general situation. You take any algebraic monoid, you embed it in the monoid of matrices, and you take the invertible elements of M. It is exactly the intersection of M with invertible matrices. Okay? And from this equality, you see that the group of invertibles of an algebraic monoid M is open in M. Is open in M. And it is an algebraic group. So the group of invertible elements is an open algebraic subgroup in the algebraic monoid M. There is a close relation, actually, of algebraic monoids and algebraic groups. And this relation becomes even closer if we assume, and we shall do it for the sequel. So let us assume for the sequel that X is irreducible, that M is irreducible. Assume that M is an irreducible affine algebraic variety. It is an affine algebraic monoid, which is an irreducible affine algebraic variety. And this G is an open subset in an irreducible affine algebraic variety. And it follows that G is connected. A connected algebraic group. And it is dense in M. So we get a big open piece of M, which is an algebraic group, and the whole M is the closure of G. Now we get the following situation. So we may consider an action of G cross G, of the doubled group G cross G, on M by left and right multiplication. So the first factor acts by left multiplication, and the second factor acts by right multiplication. Now the subgroup, the group G, the group of invertibles G, is an open orbit for this action. Open orbit for this action. And it is actually isomorphic to the quotient space of G cross G modulo the diagonal. The diagonal G is the stabilizer of the unity element under this action. We have already seen such a homogeneous space, yeah, in the case of reductive G. So in other words, an affine algebraic monoid, let me say better, an irreducible affine algebraic monoid is an affine open equivariant embedding of G. So any irreducible algebraic monoid can be considered as an open affine equivariant embedding of its group of invertibles. Remarkably, the converse statement holds. So let me call it theorem 2. The converse statement says that any affine G cross G equivariant open embedding of G is an algebraic monoid, can be equipped with the multiplication law, making it an algebraic monoid. Such that its group of invertibles is exactly the group G we started with. In other words, algebraic monoids are the same affine algebraic monoids, irreducible affine algebraic monoids. All these assumptions are exactly the same as affine open embeddings, equivariant embeddings of connected algebraic groups. Yeah, any question?
So we require the embedding is open and G is connected, right?
Yes. All the above assumptions, we keep the above assumptions. So yes, embedding is open and G is connected. Let's prove this theorem. So let's consider, so for any element in G cross G, so for any pair of elements G1, G2 in G, consider the action of the following pair, G1, comma, G2 inverse on any element of M.
Professor,
Yeah.
ask a question. And so, does the open embedding ensure that M is irreducible? Oh,
yes,
so
of course.
From the connectedness of G. Oh, I see.
It's because of connectedness of G. Yeah. So consider the action of any pair of this kind, G1, G2 inverse, on any element of M. And let us denote this action as multiplication. So by definition, we assume that this action is denoted in the following way. G1 dot X dot G2. This is just a notation. For any G1, G2 in M, in G, in G, and any X.
So I think we should assume that M is irreducible, and the open embedding does not ensure that.
By definition, when we define what is an embedding means that this variety on the right, this guy, is embedded in here as a dense open subset. So this guy is the closure of this guy. This is by definition of what is called embedding. Well, maybe I skip here some, I do not write all things, but this was in the definition of an embedding. When we discussed, spherical varieties, we defined what is an embedding. But anyway, you may say that M is irreducible. You can keep all the previous assumptions. Of course, we assume that M is irreducible here. So I denote this action by multiplication because it indeed extends, this action extends the multiplication on G. So this action extends the multiplication on G. Because if X belongs to G, to this open subset, G in M, then of course the action of this element is given by this multiplication formula. And if X is any element in M, I just use this as a notation for this action. Because we have an action, we have an equivariant embedding, so we have an action of G cross G on M, extending the multiplication action on G. In particular, if we take G2, if we take this G2 to be the unity element, so we act by the first factor, we get the following map. We get the action map from G cross M to M. Let me write this second M here for some reason. You will see the reason. We get the map from G cross M to M, this action map or multiplication map, if you like, by this notation. And similarly, if you take G1 equal to the unity, then you get the map, a similar map from M cross G to M. The action of G2 on the right, or the multiplication of G2 on the right. And both these actions, both these maps extend the multiplication map from G cross G to G. We have the usual multiplication map from G cross G to G, which is embedded in M. And we have open embeddings, of course, here and here. And these two maps, the upper arrow and the lower arrow extend the usual multiplication map on G. Okay, so since these are the maps of affine algebraic varieties, they induce the respective homomorphisms of coordinate algebras. So we get the following maps, homomorphisms, algebra homomorphisms. Let me write it here. Try to write it here. K of G tensor K of M. This is the coordinate algebra of this guy. And similarly, we have K of G. Sorry, let me write it better. K of G tensor K of G. And here we have K of M tensor K of G, with the obvious inclusions here and here. These inclusions are reversed to these inclusions because G cross G is an open subset in G cross M and in M, and both in M cross G. So there are more regular functions on the open subset than on these affine varieties, on above and on below. And here we have K of G, which contains K of M, and we have homomorphisms from here to here, and also from here to here, and from here to here. These are co-multiplication homomorphisms. Now this implies that we get a homomorphism from K of M to the intersection of these two, of this one and this one, in here, because K of M maps both to here and to here, and both these homomorphisms are restriction of this homomorphism from K of G to K of G tensor K of G. So we have a homomorphism from K of M to the intersection of K of G tensor K of M with K of M tensor K of G. And this intersection is exactly K of M tensor K of M. So this homomorphism from K of M to K of M tensor K of M gives rise to a multiplication map. M cross M to M, which extends the multiplication map on G. So we have got that M is indeed an algebraic monoid, and it remains to prove that its group of invertibles is exactly the group G we started with. It is easy. If you take any G, an invertible element of M, then the multiplication by this G, say on the left, sending X to G dot X, is an isomorphism of algebraic varieties because G is invertible. There is an inverse map, the multiplication by G inverse. And this means, this implies that there are two open subsets. The group G shifted by this G small and the group G itself. So both these guys are open dense subsets in G. Open non-empty subsets in my irreducible algebraic variety G. And since M is on my irreducible algebraic variety M, and since M is irreducible, these two open subsets intersect. And if we take any element in the intersection, we get that we have something like this: G dot G1 equals G2 for some G1, G2 in G. And this implies that G itself is equal to G1 inverse dot G2, and therefore belongs to G. So we proved that any invertible element on M is contained in G. And the converse implication is obvious because the group G itself consists of invertible elements. So it is contained in G of M. So we finally proved the whole theorem, and let me end the first half of my lecture at this point. So now we have a break, and if you have any questions, then as usual, you can ask me. So please go ahead with your questions if you have any. I see something in the chat. Let me try to answer. What is the relation of algebraic group and abelian variety? Why the latter is important in many areas? Well, I guess that sometime before I already commented on this, but let me repeat that you can define an algebraic group to be any algebraic variety equipped with the multiplication law, such that there is a unity element and any element is invertible. You can define an algebraic group like this, and under this more general definition, any abelian variety is of course an algebraic group. But let me emphasize, so the answer to your first question is that abelian varieties are particular case of algebraic groups. Abelian varieties are exactly algebraic groups which are complete or projective and irreducible. You may define an abelian variety like this. A complete or projective, it is the same for algebraic groups, a complete algebraic group which is irreducible. This is an abelian variety. But in my course, in my lecture course, I defined an algebraic group to be an affine variety, equipped with the group law such that, such that the group operations are morphisms. So under this more special definition of an algebraic group, these two classes of varieties do not intersect. So the only intersection is a one-point group, the trivial group. The answer to your questions defines on what you take for a definition of an algebraic group. Okay. Why abelian varieties are important in many areas? Well, I mean, this is how to say. Because abelian varieties are a nice class of algebraic varieties. They are algebraic varieties with a lot of symmetries because you have translation action of an abelian variety on itself. So any abelian variety has a big group of automorphisms. And for this reason, it is accessible for studying. And of course, there are many applications of abelian varieties in algebraic geometries. Well, the first class of abelian varieties is the class of elliptic curves. Elliptic curves are exactly abelian varieties of dimension 1. So why elliptic curves are important? Well, for many reasons. They even starting from number theory, from complex analysis, because they correspond to double periodic functions, meromorphic functions on the complex plane. This is a classical area. And also, if you study arbitrary algebraic curves, there is a concept of a Jacobian of an algebraic curve. Jacobian is a connected part of its Picard group. And the Jacobian of an algebraic curve is always an algebraic variety. And the theory of Jacobians has many implications in the theory of algebraic curves. So this is roughly what the answer to your second question: why abelian varieties are important in many areas.
Professor.
Yeah.
So there is a morphism from a canonical morphism from a monoid to a group that is a Grassmannian groupification. I see. Is the Grassmannian groupification a morphism between varieties?
Excuse me, I don't think I grasped your question clearly. Can you repeat it, please? Well, so what is the question exactly?
Well, we have a canonical morphism from a monoid to a group.
No. We have not a canonical morphism from a monoid to a group. We have an embedding of a group into a monoid. You mean this one?
I'm not saying this. I'm saying a Grassmannian groupification. I mean, the Grassmannian has invent a procedure to make a monoid become a group, or this only apply to commutative monoid. I will.
So you want to make a monoid a group, or I still don't understand.
Well, I think Professor, you should know that there is a procedure to make a commutative monoid into a group.
To make a commutative monoid into a group?
Yes.
Oh, well.
I think it is named the Grassmannian groupification, I mean.
So for instance, if you consider the monoid just the base field with the usual multiplication, yeah. So we have, if you remove the zero element, you get a group, right? K cross, the multiplicative group of a field.
This. I think I have to look up what is the operation named.
Okay. So then please look. Then please check what is the operation, and you can write me or write in the chat whatever. Yeah, so we can discuss. But so far, I don't understand clearly what is this construction. Yeah. But in this situation, for algebraic monoids, we have a group of invertibles sitting in an algebraic.
For any monoid, there is a Grassmannian group associated to it. I see.
Okay. So you can check this construction, and then we can look together what does it mean for algebraic monoids. I think that this construction, if it exists, is an abstract construction. It doesn't extend over algebraic varieties, over algebraic monoids in this terminology, because I mean you have some you have to require that the operations should be morphisms. Yeah, this is important, that the multiplication law should be a morphism. I don't think that this your general construction satisfies this condition.
It should be it should be yes, I mean it should be a morphism, but well, is there any I mean is there any theorem stating that an algebraic monoid can be embedded into some algebraic group as a semi-algebraic set?
I don't think so. I don't think so. But let's discuss this later because, well, maybe I got your idea, but I think that let's discuss this later, okay? Because it takes some time to discuss. Okay, so I think that the break is over and we can continue. So now we have seen in the second theorem that viewing algebraic monoids as equivariant, affine algebraic monoids, irreducible affine algebraic monoids, are the same as equivariant open embeddings of algebraic groups. Equivariant affine open embeddings of algebraic groups. The theorem 2 says exactly this. And viewing algebraic monoids as equivariant embeddings of algebraic groups, we can apply the theory of spherical varieties to this situation if the group of invertibles is reductive, because in the theory of spherical varieties, the acting group is reductive. So this leads us naturally to the following definition. So let me define what is a reductive monoid. Definition. So an algebraic monoid M is reductive if the following two conditions hold. So first we assume that M is an irreducible and normal affine algebraic variety, which we assume already in the definition of an algebraic monoid. And the second condition is that its group of invertibles, G, is reductive. So reductive algebraic monoids are a natural extension of reductive algebraic groups, or connected reductive algebraic groups. And by theorem 2, which we just have proved, reductive monoids are the same, exactly the same as affine spherical G cross G varieties with the open orbit being G itself, considered as a homogeneous space over G cross G. G cross G modulo the diagonal. We know that this is a spherical homogeneous space, even a symmetric space. And since we know that reductive monoids are exactly affine equivariant open embeddings of this homogeneous space, we see that it is the same as affine spherical G cross G varieties with this open orbit. Now we can apply the theory of spherical varieties to this class of affine spherical G cross G varieties. Recall the color data of this spherical homogeneous space, G cross G over the diagonal. Recall the color data of this spherical homogeneous space. So we can take, for the Borel subgroup, we can choose for the Borel subgroup, we can choose B minus cross B, where B is a chosen, a given Borel subgroup in G, and B minus is its opposite Borel subgroup. This will be a Borel subgroup in G cross G. And for this Borel subgroup, the weight lattice the lattice of eigenweights of all semi-invariant rational functions. The weight lattice lambda consists with all weights which are pairs minus lambda comma lambda, where lambda runs over the weight lattice of the maximal torus in B. And of course, this weight lattice can be identified with the weight lattice, with the character lattice of T itself, just embedded anti-diagonally in the double of lambda of T. Okay. We also know what are the colors. The set of colors. Let me denote the colors D1, comma, etc. DL. And these colors are the divisors, the prime divisors complementary to the big cell in G, which we described explicitly when we discussed the color data of this spherical homogeneous space. And let me recall just that the vectors in the dual space of the weight lattice, the vectors VDI bars, corresponding to these colors.
Why we choose the Borel subgroup to be B minus times B not?
Well, you can choose any, but this is convenient, for instance, to have this presentation of the weight lattice. Otherwise, we have to twist by some element of the while group here. I don't want to do this. So just check how we did this when we computed the color data for this homogeneous space. I guess it was.
I remember that. So, I mean, we choose B times B minus. It is the same, I think.
Yeah, I mean, this is just for convenience. For nice shape of several formulae, it is not essential. You can take any Borel subgroup, and then all this data will be twisted accordingly. So this is inessential. This is just for convenience. But let us keep this choice. And so we have under this identification of the weight lattice with the character lattice of the maximal torus in B, in a single B. Yeah. So the vectors corresponding to the colors in the dual space of this weight lattice are exactly the simple coroots, which I denoted by alpha I check. So simple coroots. And finally, the evaluation cone in this case, the evaluation cone is exactly the negative Weil chamber in the dual space, consisting of all vectors in this dual space E, whose pairings with all simple roots, now not roots but roots, are non-positive. This is a negative Weil chamber. Okay. All this we computed before. I just recalled it for your convenience. And now, the first two theorems which we proved today. So theorem 1, which is the affinity criterion for spherical varieties, and theorem 2, which says, let me recall, which says that algebraic monoids are the same as affine equivariant open embeddings of G, of the group G. So these two theorems imply the following theorem. So let me call it theorem 3. It says that reductive monoids with a given group of invertibles. So the set, the collection of the class of reductive monoids. Let me shift it in here to here. So maybe let me start here. So reductive monoids with the group of invertibles given a reductive group G are in a one-to-one correspondence with pointed cones say C, generated by all simple coroots and some vectors in the negative Weyl chamber, say V1, etc. Vk, such that Vi belong to the negative Weyl chamber. So there is a one-to-one correspondence with the reductive monoids with given group of invertibles and colored cones of this type, generated by all simple coroots and some vectors in the negative Weyl chamber, finitely many vectors in the negative Weyl chamber. So the cones should be pointed, of course. So this theorem immediately follows from the previous two, because theorem 2 says that reductive monoids with the group of invertibles G is the same as a fine G cross G equivariant open embeddings of G. Yeah. And this
theorem 2, theorem 1 is the first theorem today.
Yes, theorem 1 is the first theorem today. So I just said that reductive monoids with given group of invertibles G are the same as affine spherical G cross G varieties with open orbit G. But affine spherical varieties are described by the first theorem, by this theorem. They correspond one-to-one to the cones of this type with these conditions. Yeah. And these cones are generated by the vectors corresponding to all colors. This means by all simple coroots, and by some vectors sitting in here corresponding to G-stable prime divisors. And these vectors are taken from the evaluation cone. So from this cone V. So this is exactly the reformulation of theorem 1 in view of theorem 2. This correspondence is a reformulation of theorem 1, taking into account this computation of colored data for this homogeneous space. This theorem is due to Weinberg. Let me write it here. So this theorem is due to Weinberg. Of 1995. But in fact, his proof didn't use the theory of spherical varieties. His proof was different and maybe not quite straightforward. A proof in the spirit of what I have just said as an implication of the theory of spherical varieties was given later by Alvaro Ritatore, three years later. So let me write his name here also. It was in 1998. Okay. So this theorem gives us a full classification of reductive monoids, a complete classification of reductive monoids. And this correspondence between reductive monoids and some special pointed cones is not just a formal bijection. One can recover efficiently a reductive monoid from its cone in the following way. So let me write it as a remark. First note that the coordinate algebra of the monoid M, since it is a spherical variety, it is a direct sum of irreducible submodules, which I denoted, irreducible submodules in the coordinate algebra of M or of G, which is an open subset in M, corresponding to highest weights lambda, where lambda range over the lattice vectors in the dual cone. We have already seen such kind of decomposition. And this guy, the irreducible G cross G submodule in the coordinate algebra of G, is exactly, let me recall it for you because we already discussed it, is exactly the space of matrix entries for the respective is irreducible representation of G. So the coordinate algebra of an algebraic monoid, of a reductive algebraic monoid, is the direct sum of certain spaces of matrix entries. Not all of them, but those corresponding to irreducible representations of G whose highest weights belong to this dual cone. Only this. So the condition that the weight lambda belongs to the dual cone means exactly, so this holds if and only if all matrix entries of the respective irreducible representations of G, of the respective irreducible representation of G, so associated with this lambda, we have, of course, an irreducible representation of G in the vector space V of lambda. We have such a homomorphism, yeah, for any highest weight lambda, for any dominant weight lambda, not necessarily belonging to this C check, but this lambda belongs to C check if and only if the matrix entries of this representation extend to regular functions on the whole M. So this means that we extend this map to the map from M to linear operators on V of lambda. So this homomorphism, the representation of G, extends to the representation of M in endomorphisms of V of lambda. In other words, the coordinate algebra of a reductive monoid consists, is spanned by the matrix entries of those representations of G which extend to M. Okay? This is a precise description of this coordinate algebra. And now how we can describe these matrix entries? So which representations of G extend to M? Well, for instance, you can check, you can take a finite set of generators for this semi-group. Say, suppose lambda 1, etc., lambda m are the generators of.
Professor, so sorry, I have asked a question. So
yeah, please. Okay.
So in the Broughette decomposition of the algebraic group G, we have that every B invariant divisor of G is generated by a simple reflection, right? I mean.
Yes. We have discussed this, right? Okay.
So is simple reflection the number of simple reflection equal to the number of simple root?
Exactly.
Why is this case?
Why what?
Why is this case? Why is every simple reflection?
Well, I mean, just by definition, what is a simple reflection? Simple reflections are by construction associated with simple roots.
A simple reflection is a reflection with respect to simple root, right?
Exactly, exactly. Well, actually, there is, in fact, of course, there are many things to discuss if we discuss the structure theory of reductive groups or semi-simple groups, all this stuff with root systems, while groups, simple reflections, Brouillard decomposition. It is somewhat beyond my course. It is some basic theory of algebraic groups. So I just recall basic things, basic facts, and do not go deep in them. I assume you know to a certain extent all this material. But of course, if you want to go into proofs and into more details, you have just to take some textbook in algebraic groups. For instance, Humphrey's book is okay, or Springer's book, the references which I gave before. Okay. Well, let's continue. So if we take a set of generators of the semigroup of lattice vectors in C check, then as we have discussed before, this implies that the coordinate algebra of M is generated by the respective spaces of matrix entries. So generated by the direct sum of matrix entries of V of lambda 1, etc. V of lambda m. So if these lattice vectors generate the semigroup of lattice vectors in C check, then the respective irreducible submodules generate the coordinate algebra. By the way, the converse implication doesn't hold. So let me just mention that the converse implication doesn't hold in general. So,
Professor, I want to see the last thing. Sorry.
The last page?
Yes, just a moment.
Okay.
Yes. Okay.
Okay. So then we go on. So the converse implication doesn't hold because it may happen that actually this coordinate algebra is generated by a smaller subspace of matrix entries. We shall see it in an example. But let me also say that the coordinate algebra of M is generated by the collection of matrix entries corresponding to a finite set of irreducible G modules, V of lambda 1, V of lambda M, if and only if this holds, if and only if, now in both directions, any lattice vector in the dual cone satisfies the property that the respective irreducible G module is embedded as a submodule in the tensor product of some of these V of lambda i's, V of lambda I1, tensor, etc., tensor V of lambda I, say, big N, for some I1, I big N in the range of from 1 to M. This is because we know how the spaces of matrix entries multiply. So if you multiply one space of matrix entries with another one, then you get the direct sum of all spaces of matrix entries corresponding to the irreducible summons of the tensor product of one irreducible submodule with another one. And the coordinate algebra is generated by this subspace if and only if when we multiply this space with itself many times, we get the whole coordinate algebra. This means that any space of matrix entries of this kind, with this highest weight, with this condition, can be embedded in the tensor product of some of these guys. So this is the same thing. And also, Another equivalent condition is that, so this also holds if and only if. Another equivalent condition is that the monoid M is exactly the closure of the group G in its representation given by the direct sum of these irreducible representations corresponding to the generators of the coordinate algebra. So let me write it explicitly that this property that K of M is generated by this space of matrix entries, this property is equivalent to saying that M is the closure of G in the space of endomorphisms, of the direct sum of these irreducible representations corresponding to the generators of the coordinate algebra. Of course, you have a map from G to this space, and this map extends to the map from M to this space. And I say that this map from M to here is a closed embedding if and only if this coordinate algebra is generated by this space of matrix entries. Because just because a map between affine varieties is a closed embedding is if and only if the inverse map of coordinate algebras is surjective. And to say that the coordinate algebra of this space of endomorphisms maps surjectively to the coordinate algebra of M is exactly to say that this coordinate algebra is generated by the space of matrix entries corresponding to this representation. So we conclude that we can recover explicitly the monoid M from its cone C by choosing the generators of the respective coordinate algebra, which can be taken just maybe a bit bigger than it suffices to take. But we can take for generators just the spaces of matrix entries corresponding to the generators of this semigroup. So starting with the cone, we pick the generators of this semigroup. Then we take the respective spaces of matrix entries. They generate the coordinate algebra. We can take even a smaller space if we are lucky. But anyway, if we take this space of matrix entries generating the coordinate algebra, then M is recovered as a submonoid in the endomorphisms of this representation space, given by just taking the closure of the group G acting on this representation space. This is an explicit construction of a monoid M from its cone.
Professor, I want to ask a question.
Okay.
I think the space of matrix entry is the image of V lambda star tensor V lambda. I think it is
yes.
Not.
You are right.
So why it is equal to the invariant the G sub module with respect to lambda? Where is lambda star? I mean.
Well, I mean, because on this space there is an action of G cross G. So what are matrix entries? Matrix entries are functions on G, right?
Yes.
And on these functions, you can act by G cross G, by a left translation of an argument and by right translation of an argument. So we have a representation of G cross G on this space. And a representation of G cross G is a tensor product of two representations of G. Here, V lambda star comes. V lambda star comes from the action on, on the right.
So it is the double action, I mean.
Yes, yes, this is because of the double action. Okay, so now let me turn to an example. Let me consider an example. For the example, I will take this basic example. Let me take the monoid of all n by n matrices. The monoid of all n by n matrices over the field K. In this case, its group of invertibles is, of course, GLN of K. Let me consider the following functions on the group of invertibles on GLN. So these functions will be just the upper left corner minors. So let me try to draw a matrix. Excuse me. Okay, so we can see the functions of this form. Well, something like this. We take an upper left corner minor, and the respect, well, leading, if you like in other terminology, it is leading principal minor, yeah? And we take, let me denote it by delta K. So we assume that the size of this minor is K by K. And these functions, these are polynomial functions, regular functions on G. This delta K's are polynomial functions on G, which are semi-invariant with respect to the Borel subgroup B minus cross B, where B is the usual subgroup of upper triangular matrices, and B minus is the opposite Borel subgroup of lower triangular matrices in GLN. Yeah, and the eigenweights of these functions are, in our previous notation, the eigenweight is a pair corresponding to the character of B minus and character of B. So a pair of characters of T. And this is the following pair of characters: minus epsilon 1 minus etc. minus epsilon k, comma epsilon 1 plus etc. plus epsilon k, where these epsilon i's are the same as before. Epsilon i's denote the diagonal entries. So the maximal torus here is the subgroup of diagonal matrices, and epsilon i's denote the diagonal entries of the maximal
delta
torus.
K is the determinant. Is the determinant of this principal minor, right?
Well, in my feeling, the minor is already a determinant. The minor is the determinant of this submatrix. Yeah. So delta K is the determinant of this submatrix. Is the determinant of this submatrix. And the eigenweight is like this. So actually, these minors are exactly the equations of B-stable prime divisors in this case. So B-stable prime divisors, B-stable prime divisors B-stable prime divisors are the following. So D1, etc., Dn minus 1, Dn, where dk is exactly the set of matrices where delta k vanishes. So the complement of all these divisors is the big cell in GLN. The set of all matrices with non-vanishing leading principal minors can be taken to the unity matrix by multiplication with lower triangular matrix on the left and with upper triangular matrix on the right. So this complementary set the non-vanishing locus of all delta K's is a single B minus cross B orbit. It is the open orbit, the big cell. And the complementary divisors are these decays. So the first n minus 1 of these decays are the colors. So these are colors. And Dn is a G-stable prime divisor. It is just the set of all degenerate matrices, G-stable prime divisor. Now, the eigenweights of this delta K's, it is easy to see that the eigenweights of this delta K's generate the weight lattice of G. Yeah. And if you look at the respective at the vectors, if you look at the vectors corresponding to these B-stable prime divisors, if we look at these vectors V sub dk bar, then their pairings with the eigenweights of delta K's, so their pairings with epsilon 1 plus etc. plus epsilon j, these will be Kronecker deltas. So this pairing is equal to 1 if j equals k, and to 0 otherwise. Because this pairing is exactly the vanishing order of the respective function delta j along the divisor delta k. So if j equals to k, then this function is exactly the equation of this divisor, and the vanishing order is 1. And if j is non-equal to k, then this function doesn't vanish on delta k, and the order is 0. So these pairings are of this form. And from this, we easily deduce that the vectors v sub dk bar are of the following form. V sub dk bar is equal to epsilon k star minus epsilon k plus 1 star for k smaller than n, less than n. And v dn bar is just epsilon n star, where this epsilon I star are exactly the vectors in the dual basis of epsilon 1, epsilon n. So epsilon 1, epsilon n form the basis of the weight lattice, and epsilon I star form the basis in the dual vector space in which these vectors sit. So we have this tuple of vectors, v sub dk for all k, and this vector generate the cone C. These vectors correspond to all B-stable prime divisors, yeah? So they generate the cone C corresponding to the reductive monoid M. So the cone C in this case is generated by all these vectors, epsilon 1 star minus epsilon 2 star, etc. Epsilon n minus 1 star minus epsilon n star, and finally epsilon n star. This is the cone C, and the dual cone C check is clearly generated by the vectors of the dual basis. So it is generated by exactly the eigenweights of delta K's. So these vectors will be the dual to this tuple of vectors. Epsilon 1 plus epsilon 2, etc. Epsilon 1 plus, etc. plus epsilon n. So this is how these cones look like. Also, we can observe that these vectors generating the dual cone, the vectors on the rays of this cone are exactly the generators of the semigroup C check intersect with lambda, the semigroup of lattice vectors in the dual cone. So in this case, this cone is what is called strictly simplicial. It is generated by linearly independent lattice vectors, which also generate the semigroup of all lattice vectors in this cone. And by the remark before, which we made before, by this remark, we can say that the coordinate algebra of M is generated by the set of matrix entries corresponding to the representations of GLN with these highest weights. So we take all representations of GLN with these highest weights. We take the spaces of matrix entries for these representations, and the algebra generated by all these matrix entries is exactly the coordinate algebra of M. But in this case, we can see, so let me write it here on the next page, that K of M is generated by the space of matrix entries of V of epsilon 1 plus etc. V of epsilon 1 plus etc. plus epsilon n. But in this case, as I said, the coordinate algebra of M can be generated by a smaller set of matrix entries. We can just take the representation with the highest weight epsilon 1, which is just the standard representation of GLN in the n-dimensional column space, K to the n. The highest weight vector in here is the first basic vector in the standard basis. E1 has the weight, it is a B semi-invariant vector, it has highest weight epsilon 1. This is the highest weight vector. And if we take the tensor power, say kth tensor power of this standard representation, this kth tensor power contains the kth wedge power. Of the standard representation. And this kth wedge power is actually an irreducible representation, of highest weight V of highest weight epsilon 1 plus etc. plus epsilon k. The kth wedge power of k to the n of this script k to the n is exactly the space of skew symmetric tensors of degree k on the standard vector space, and it is irreducible with highest weight vector given by the wedge product of the first two basis vectors. This wedge product will be, again, B semi-invariant, and its highest weight will be exactly this weight. So we see that all irreducible representations of GLN corresponding to the generators of the coordinate algebra of M actually lie in the tensor power of this single representation. And by the discussion which we conducted here, by the discussion of generators of K of M, so it suffices to take a single representation V of epsilon I, and all other representations will be embedded in its tensor power, in its tensor powers. So we conclude that the coordinate algebra of M is generated
Professor,
by the space. Just let me finish. I will reply in a minute. The coordinate algebra of M is generated by the space of matrix entries corresponding to this single irreducible representation V of epsilon 1 by the previous discussion. Of course, this is obvious from the very beginning in this example, I mean, because the monoid of all n by n matrices, its coordinate algebra is generated by the matrix entries of these matrices. And these matrix entries are exactly the matrix entries of the representation of K in the space K to the n. So it is obvious from the very beginning that in this example, the coordinate algebra is generated by this space, but I just wanted to put it in the general picture, yeah, to make it fit the general description of generators of the coordinate algebra of any reductive monoid. So this is this basic example. Now, what was your question?
I mean, why is the irreducible representation with respect to epsilon 1 has n-dimensional? I mean,
well, you just take the argument is in the opposite direction. You just take this representation, yeah, the representation of GLN in K to the n. You observe that it is irreducible, and you observe
the representation of GL. Oh, this case G is GLN. Oh, I see.
Yes, so, yes. So this is a representation of GLN. It is irreducible. And this guy is the highest weight vector in this irreducible representation. And this is its highest weight. Okay?
Well, I mean, the representation of GLN on the n-dimensional affine space. I mean, why is epsilon 1 the highest weight? I mean,
well, because what is the highest weight? I mean, first of all, you observe that this E1 is a highest weight vector. This means it is B semi-invariant.
I remember we choose a Borel subgroup. Oh, I see.
Upper triangular matrices.
If we choose other Borel subgroup, then the highest weight could change to epsilon 2.
Of course. The highest weight depends on the chosen Borel subgroup. We have to choose some of them, any of them, and fix this choice. Yes. Okay? Okay, so I see that my time is over, and let me just put some concluding remarks and gives you an exercise to finish this lecture. So first of all, the theorem, this theorem 3, which we proved here, the description, the classification of reductive monoids with the given group of invertibles, has the following corollary, which is not obvious from definition. I mean, the corollary is the following. The only algebraic monoid with the semi-simple group of invertibles not just reductive, but semi-simple. The only algebraic monoid with a semi-simple group of invertibles is this group itself. So semi-simple algebraic group admit no non-trivial equivariant embeddings into algebraic monoids. The only algebraic monoid whose group of invertibles is semi-simple is this group. This immediately stems from the classification. So the proof is very short, actually. You just observe that for semi-simple G, semi-simple G, if you take any vector v in the negative well chamber, well, non-zero, the cone spanned by this vector and all simple coroots will be the whole vector space E. So this cone cannot be pointed. Let me draw it on the picture to make the picture clear for you. So you have something like this. You have the negative well chamber, say here.
This is the property of semi-simple algebraic group, right? Or semi-simple group, right?
Right. This is a property of semi-simple algebraic groups, not just reductive, but semi-simple. You have the negative well chamber, and you have the simple coroots, yeah? So say this one, and maybe this one, simple coroots. Excuse me. So these two vectors are simple coroots. These are alpha i's check, yeah? And this is the negative well chamber. As usual. Negative well chamber. V. And if you take any vector in the negative well chamber, say this one, this small v, any vector in the negative well chamber, then the cone generated by this vector and all simple coroots will be the whole vector space. So this cone cannot be pointed. It cannot correspond to any algebraic monoid, to any reductive algebraic monoid. The only case when the cone will be pointed is if you take no vector v here, if you take only simple coroots. And in this case, you get just the group G itself.
Well, for semi-simple group, the coroots span a solid.
Exactly. This is the reason. Yes, exactly. This is because for semi-simple group, the simple coroots span the solid cone, and any vector in the negative well chamber is opposite to this cone in a sense. So if you add this vector to the generators, then you get the whole vector space. This is the peculiar property of semi-simple groups, not just reductive, but semi-simple. Okay, and finally, let me give you an exercise.
Well, Professor, I mean,
okay.
The validation cone is the negative well chamber, right?
Right.
So this means that the simple coroot belongs to the positive well chamber. Positive.
No. The simple coroots span the cone dual to the positive well chamber. So if you take the opposite to the negative well chamber, so if you take something here, you will get the dual cone. Well, the dual cone to the cone generated by simple roots, not simple coroots, because they are in the dual space. We just put them sometimes on the same picture.
So the coroots is sitting in the dual of the cone spanned by the simple root, right?
Yes. The coroots are sitting in the dual space, But if we speak about cones, if you take the cone spanned by simple roots, then the dual cone will be the positive well chamber, sitting in the same space where the coroots sit. So the dual cone will be opposite to this green cone.
So what is the relationship between the positive well chamber and the coroot? No relationship.
Well, I mean, you can say that the cone spanned by coroots contains the positive well chamber.
Oh, contains.
You can say like this. contains. But actually, there is no duality relation because they sit in one and the same space. The dual cones sit in mutually dual space. But in this case, they sit in one and the same space. There is the duality relation between the positive Wild chamber and the cone generated by simple roots.
I know that. So the semi-simple condition means that the cone generated by simple co-roots are solid and they lie in the a positive dual half space, right?
Yes. You can say like this. Well, I see that I'm over my time. Let me just finish the lecture by giving you an exercise, and then I can answer further questions, should you have any questions. So this second exercise, which I give to you, will be about algebraic monoids, reductive monoids. Let's take the group G, BSL2, cross K cross to the square. And this group acts naturally on the space V, which is the sum of two copies of K to the square, on which SL2 acts in a natural way, and K cross square acts by dilations on each copy. So you have independent dilations on each copy of this direct sum, of this K square in this direct sum. And this is the action of K2 square. So let us take for M the closure of G in endomorphisms of this vector space. This is an algebraic monoid. It is a reductive algebraic monoid. So the exercise is first to check that M is normal. Secondly, find the respective cone corresponding to this monoid. And thirdly, describe G cross G orbits in M. The open orbit will be G itself, but what are other orbits? This can be done via the theory of spherical varieties, because we know the description of orbits in terms of colored faces and so on. Okay, so now the lecture is over, and if you have still questions, then I can.
Dilation means that multiplication on each coordinate, right?
Yes, not by each, not yeah. I mean this is the direct product of two copies of K star, and the first copy of K star acts on here by multiplication, while the second copy of K star acts on here by multiplication. So these two copies of K
SL2 acts on?
SL2 acts naturally because SL2 is 2 by 2 matrices with determinant
SL2
ones.
acts on both entry, right?
Exactly. Yeah. Well, are there more questions?
Well, normality here. Well, how can we check normality?
How can we check normality? It is a good question. Well, I think that you can try the following. You can try to compute the coordinate algebra of this M. Yeah, I mean, I can give you some hints. You can try to compute the coordinate algebra of this M just by arguments of this type. So you have finitely many irreducible representations, in this case, you have exactly two irreducible representations. These summands of this direct sum are irreducible representations of G. And you can try to compute some of the tensor products, yeah? It is easy because for tensor products of representations of SL2, we have the Clebsch-Gordan formula, which appeared already on the first lecture. So you can try to compute the tensor products and observe which kind of irreducible representations you get sitting in these tensor products as irreducible summands. And all these, if you take all these irreducible representations, you get the submodules in the coordinate algebra of M. So you can find the description of the coordinate algebra of M from this tensor product decomposition. You can find its decomposition into direct summands of this type. Now, if you pick all respective highest weights, all these lambdas, you look at the cone spanned by all these lambdas. And this cone, of course, will correspond to some algebraic monoid. And the coordinate algebra of this algebraic monoid will consist of all lattice vectors, will consist of all summands corresponding to all lattice vectors sitting in this cone, yeah? But if you get already all lattice vectors from this tensor product decomposition, well, when you compute the tensor product decompositions, you will get these lambdas, which will be lattice vectors. If you get all lattice vectors in the dual cone, then this will mean that the coordinate algebra of your M, yeah, the coordinate algebra of your M, the coordinate algebra of your M coincides with the coordinate algebra of some normal algebraic monoid given by this kind of decomposition. Therefore, this M will be normal. So the normality condition means that the coordinate algebra of M decomposes with such a direct sum corresponding to all lattice vectors in some cone, yeah, without any holes. If it is the case, then you will get normal algebraic variety, normal monoid.
Why is this equivalent to normal? I mean, normal means that there is no singular locus that has codimension 1.
Yeah. Of course. I mean, I don't want to get to the back to the definition of normality. I want to use a previous theory. So if you prove that the coordinate algebra of your monoid has this type of decomposition, yeah? If you prove that the coordinate has this type of decomposition corresponding to all lattice vectors in some cone,
yes,
this will mean that the coordinate algebra of your monoid coincides with the coordinate algebra of some other maybe monoid corresponding to this cone. Because we know from the classification
they are one-to-one correspondence.
Exactly. We know from this classification that to any cone of this form, there corresponds some algebraic monoid, normal algebraic monoid, whose coordinate algebra decomposes in this way.
Oh, so they are the same.
Yeah, so they are the same. Exactly. This is the idea how you can prove normality, how you can check normality. More questions?
But there are questions. So I mean, just now we discussed the irreducible representation of SL2, but there is dilations.
The dilations are easy to handle. Dilations do not essentially impact in tensor product decomposition because you just take tensor product decomposition for the representations of SL2, and then you count how many copies. You decompose tensor products of representations in here and in here. you remember how many copies of this guy you take and how many copies of this guy you take. And then if you want to compute the action of this guy, then you just count how many copies of this guy you take, and you take the respective multiple of the first weight corresponding to the first factor in here, and similarly to the second sound. So it is easy to take into account the action of dilations. You just get some additional dilation action on this irreducible summand, which can be easily counted from how many copies of the two, how many copies of these two summands k square you have taken in here. Okay, did I answer more or less? Well, more questions? It seems there are no more questions. Then let me stop sharing the whiteboard. And see you all on Wednesday. I hope to see you all on Wednesday. We are close to the end of our lecture course, so we have lectures. We have the lecture on Wednesday and 2 lectures on the next week. And during these lectures, we shall. I hope to have time to discuss some further applications of spherical varieties and maybe some piece of general theory which I need for that. But let us see.
Professor, about the exercise, can I hand in the exercise after the lecture is over? I mean, maybe.
Well, it is up to you. I mean, I do not put any time restriction on exercises, on when you send me your exercises. But let me recall that we agreed that solutions of exercises are a part of final grade. Yeah. So you have to save time, to have enough time to solve the exercise. It should be done before the exam, of course, because yeah,
the exam will not immediate after we end the course.
No, I mean, of course, no, not immediate. I mean, you need to have some time for preparation for the exam, of course. But this I have to consult. I have to consult with Huhan, maybe with the secretary in your university about the date of the exam, because I don't know your schedule, the schedule of your exam session. Maybe there are time limits for the date of the exam. I have to figure out this.
Oh, thanks.
Maybe Huhan can already say something about that. I don't know. But anyway, we shall discuss the date of the exam after the lectures will be over. Next week, I mean. Then we shall discuss the date of the exam, and you will have time before the exam to solve the exercises, of course, and to prepare for theoretical material on the exam. Okay?
Thanks, Professor.
You are welcome. So if there are no more questions or comments, then maybe let's finish our today's meeting, and I hope to see you all on Wednesday. Bye-bye.